is an example, and this is the an example I kept in my Engineering Dynamics course companion. And I like this example because I use this one in multiple classes. We use this in this class, class 6. I believe it's might be in class 8, and it might be in class 10. All right, so we use the same example 3 different times. So here we have this force that's applied to this block, and that force is going to make the block go up the slope. Now I'm going to skip over a step where we might want to, for just being safe, check and see that this force actually will make this thing go up the slope, because there could be a static friction that you apply this force, and that static friction is enough so this thing doesn't move at all. Or this force could be so small and the friction not sufficient enough, even though you apply this force, the weight and the angle and so forth and the lack of friction could make this thing slide down. So you might want to do a due diligence and do like a check and see if this force is enough to unbalance the static force and break free, or enough to overcome that weight. But I think because of the nature of the problem, we can assume it is going to move. So I'm going to skip over that step. Okay, so there's a 50-pound force, and it's applied to the block. The block weighs 25 pounds and starts from rest. And the position is 25 degrees right here on an inclined plane. Static friction 0.25. We don't need it because we're going to assume it moves. And kinetic friction is 0.2. And the force applied to the block is at 15 degrees from horizontal. So that's this guy, this theta 2. Determine the distance up the slope it travels when it reaches 3 feet per second. Right, so it's starting from rest. So let's check that out here. And we have all of that there. That's good enough for us. So what I want to do is okay, so in this situation here, let me just go ahead and write the free body diagram and the inertial body diagram. Sometimes I accidentally call IRD, and I mean IBD. Now, a good strategy when they have a problem like this is to turn the axes. That helps to isolate the normal forces into one direction, which is really useful to us. So we move our axis, and I decide I'm going to call it y prime, x prime, and y prime. It's just good practice. So I draw the body, and now I start applying loads to it. Well, one load that's definitely going to happen to it is weight. Weight is coming down. And I'm going to draw in, right? So here was the directions of stuff. And if we had taken a look at this thing, we could have drawn this lightly. We would have seen that's the angle right there that we have rotated this right here. So that's actually that angle of rotation is right in there. Okay. We're also applying a force right here, this P. And I'm going to draw a horizontal line so I can keep this thing straight. So I can see that we also, not only do we have an angle due to the slope of this, but we also have an angle with the way this is formed. So I went ahead and I wrote P right in there. And that's going to be my theta 1. This is my theta 2 right in here. And I might even want to include right in there, right there. That is going to be actually theta 1, right? So we can see that this is actually theta 1 plus theta 2 when we start to do it in our direction that's aligned with the x prime. Other forces we have to worry about, well, this thing is pushing back up on it. There is a support force, if you will. This F, I call it Fn. And then we have a friction force. Now we're going to ask ourselves, which way does the friction force go? That's a common problem. Which way does it go? Well, okay, if we know, we're assuming it's going to move upwards this way, so the friction force is going to resist the motion. So the friction force is going to go in the opposite direction motion right there. So there you go. So there's all, and I forgot to put the W right there. There you go. There are all the forces that are acting there on the left-hand side. And then we take a look on the right-hand side. Well, what is the motion? Well, we're going to have mass times acceleration in the x prime direction. Is there going to be any acceleration in the y? Well, no, it's not going to lift off of the thing. It's not going to pass through the slope. So this is all that's on the left-hand side, on the right-hand side. Sorry. Okay, so now we've accomplished our FBD and our IBD. We've methodically thought our way through as we started to add all of those elements on there. Now, what's going to be useful to us is to find the sum of the forces in the y prime direction first. So the sum of the forces in the y prime direction. And we could say it equals ma y prime, but it doesn't accelerate, so it's a statics problem in the y prime direction. That's why we turned the thing, so it makes it like a little bit easier. So when we apply that force, and I decided to put this as I went through here, I used variables, and then I started feeding numbers into there. So we have P in the y prime direction, but it's going in the negative y prime direction, going downwards, but it's going to be the sine, and it's going to be the theta 1 plus theta 2, right? Now we're also going to have the weight of this thing is going to come partially in the y direction, but only the cosine of theta 1, right? And it also is going in the downwards direction, W, and we take a cosine of theta 1. The only thing left here in the y direction is going to be a positive Fn. So that's the normal force. So we could solve for Fn. And if we do that, we have the 50 times the sine of, 25 plus 15, what is that, 40? And then also plus the weight, and this is pounds, right? So it's already, we don't have to deal with anything with the slugs, with anything of it just yet, but we will. And then the cosine, and then this is just of the 25. And if we run through there, we get 54.80 pounds. We're going to use that to find the friction force right here. So our friction force we know is mu kinetic friction times normal force, or 0.2, is that, yeah, 0.2 times our, what do they say, 54.80. So we have 10.96 pounds. Now we do this in the sum of the forces in the x prime direction. It's going to be equal to mass times acceleration in the x prime direction. And I like to, I think this is a good habit, declare which is positive. I should have declared it positive up here too. All right, declare what positive is going to be. And if we do that, we're going to get, I'm going to say that it's going to be P times the cosine of theta 1 plus theta 2. We actually know what that value is, but that's okay. We'll do that. We're going to see that's going to be negative W times the sine of theta 1 minus FF, and then we have nothing over here, right? So now we're going to say equals, right? So that was everything on the left-hand side corresponding to him, which corresponds to that. And now here on the equals, we're going to have the mass, and we're going to have the acceleration. So let's stick some numbers in there. We have 50 cosine of 40 minus 25, right? Did I get that right? No, wait a minute. I I did something wrong up here. I wrote that wrong, but I knew better. That was 25. Why didn't you catch me? Oh, you will. You probably did. You were like yelling at the thing, going, "This 25. It's 25." I did all the right other stuff right in here, but I just wrote that down wrong. What are you gonna do? Shoot me. And then that's going to be minus a 10.96, and that's going to be equal to. Now we're going to take the mass. Right, 25 and divide by 32.2. So anytime you need mass, take the weight and just divide by 32.2. Don't even start like fussing about it. And that's x prime. Now something I want to do right here. If I just take a look at this right in here, what I can do is calculate what that value is, right? And if that's something that's positive and non-zero, that means it was moving up the slope, right? And actually, we should probably have replaced that friction with the static one, but I think we're okay right there. But anyway, we could kind of see, this is what the net force is. This is the net, there's not enough force to keep it in equilibrium. It's the force that's greater than the thing for equilibrium, right? So that'd be 50 and 40 cosine times, right? So that one is 38.30. That's the thing that's driving it up the slope. Some of this is the 25 pounds at the 25 sine times. So there's a 10.57 that's trying to move it down the slope. That's part of the weight. We also have the 10.96, right? And both of those things are subtracting out, right? So what we have is a net upward force of 16.78. That's the net force. And that net force is going to cause acceleration. So this is like a 16.78 is the net force. So when we calculate this out right here, we're going to get 21.61 feet per second squared. Now remember that free fall would be 32.2 feet per second squared. So this thing's booking up there. It's going up, not quite as fast as the equivalent, not fast, but acceleration as you would be with falling down. But it is moving up there pretty quickly. So, but we have to look back at what we were asked. It said determine the distance after to reach 3 feet per second. So now we go back to our kinematics, and we're looking for distance, and we have acceleration. We were told velocity. We want to use this equation. And I'm going to say delta x in this case. It's a delta x prime, right? So it's starting from rest. Its velocity, we want to get is 3 right here. This is 0 squared. 2. The acceleration is 21.61. Delta x. So how far? Or actually, they use delta s right in here. So maybe we ought to be consistent with the way that the problem was written, huh? What do you say? Sure. Delta S. There's no prime in there, so get out of there. So delta S. So our delta S, according to this, is going to be 0.2083 feet. Well, you know, that's kind of a small amount of feet. I know generally we want to give the answer in terms of the units that we were given the problem. So a lot of times we will do this in terms of, we were given feet and that kind of thing. So we were given feet per second, so might as well. But here, let's go ahead and just turn this into inches. What do you say? So multiply it by 12, and we get a nice even 2.5. Actually, it's 2.499, but I'll just go there. So it's going to move up 2.5 inches. Not going to move up very far before it reaches that 30 feet per second because of the offset in the forces. But we're going to use the same problem again and take a look at it for comparison, just to kind of prove to ourselves we can use the other kinetics methods. So let's see, how long did that take? That was about a 15-minute problem. That's good to know.